Hello and welcome to today's webinar, Protecting Current Transformers Against Open Circuit Conditions. Let me introduce you to our presenters. So firstly, my name is Gemma Shackleton and I'm a marketing manager at M&I Materials. Besides handling the introductions today, I'll be looking at the questions coming in from you so that we can put these to the team at the end of the session. Next up is Dominic Cole, our commercial manager for specialty products at M&I. Dom has a wealth of industry experience, including technical roles, electronics manufacturing, and design and commissioning of high-end hardware and software systems. Some of you joining us will have no doubt already met Dom. He spends a lot of his time developing key partnerships with leading relay and substation OEMs. Also joining us today is Dr. Tom Galvin. Tom is the lead scientist at M&I Materials, and he works closely with the Metrosil team on design and material science research. Tom joined the team after completing his PhD in materials engineering, which was based on structural carbide materials for the nuclear industry. I'll now hand over to Dom, who can get us underway. Over to you, Dom.
Thanks, Gemma, and thank you all for joining us for this Metrosil webinar. Today we're going to look at Metrosil Current Transformer Protection Units, or CTPUs, and their role in protecting the secondary winding of current instrument transformers, known as CTs, during open circuit conditions. We'll also look at what the IEEE standard is for CT protection and how we exceed this standard. And there are so many reasons for an open circuit to occur on a secondary side, from accidental removal of the burden during maintenance, for example, joint problems or damage to cables during excavation works. In this slide, we can see wireframe drawings of a single-phase and three-phase variants of Metrosil CTPUs, and our range of devices, standard devices shown at the table on the right-hand side. And also to say we can also produce custom devices for your CT. So why choose Metrosil CTPUs? Well, the CTPU name and concept was designed by Alstom power engineers back in the 1980s and was specifically designed with Metrosil varistors due to their unique semiconducting properties and in-service resilience. We have many in-service devices for over 40 years and can trace our history back to the invention of varistors almost 85 years ago, to this year in fact. So as we know, CTs are used to transform current, usually from a higher value into a proportionately lower current value, providing ammeter instrumentation and the means for protection and control. They're used worldwide to monitor high voltage current in power generation, transmission and distribution lines for power plants and substations across national grids. For this webinar, we're using this example here of a high impedance differential relay scheme, which shows CTs on either side of a transformer, and a protection relay, which will operate if there's a difference and imbalance between the CTs. So Tom will now look closely at CTs.
Thanks, Dom. So, as I'm sure most of you know, a CT produces current in its secondary winding, which is equal to the current flowing in the primary divided by the number of turns. In doing so, the current transformer reduces a high current to a lower value and therefore provides a safe way of monitoring AC transmission lines, which is accurate so long as the core of the CT doesn't saturate. CTs are typically connected to some monitoring equipment, which along with the bus bars provides an impedance, commonly called the burden. Total impedance value of the burden is what sets the operational voltage of the system, as the CT will always try and maintain the current flow. However, a CT that is open circuited, or in other words disconnected from its burden, acts like a CT with an incredibly high impedance burden, so the CT instantly becomes a step-up transformer, raising the voltage across its output until arcing and breakdown occurs between the windings. This overwhelming of the insulation voltage and arcing of the CT windings not only damages the actual CT, which could require replacement or maintenance after, but it's been known to actually cause CTs to catch fire if the insulation ignites. This could potentially lead to the substation, transformers, or whatever assets are being protected being taken completely out of action. Such fires can be devastating if the CT is monitoring a power transformer, especially if the transformer is filled with mineral oil. Now, another dangerous scenario from these high voltages is the shock hazard potential to maintenance engineers, especially if a CT is accidentally disconnected during inspection or maintenance.
So Metrosil CTPUs provide permanent protection against an open circuit condition without the need for user intervention and can remain in service for many years. As mentioned, we have millions of Metrosil devices well established and trusted in power networks across the world, especially in oil and gas and nuclear industries where CT protection is classed as critical. For those that don't know, the Metrosil brand comes from a famous British electrical manufacturer in the 1930s called Metropolitan Vickers, who were based in Manchester near to where the M&I Materials factory is now. The SIL part comes from silicon carbide, and that's the semiconducting material from which our varistors are made. I'll hand you over to Tom again, who will explain more about our unique SiC material and how this works.
Yeah, thanks, Tom. So any of you that have seen some of our other webinars on Varistor Essentials might have seen this already, but I'll quickly cover it for the benefit of those who haven't. So Metrosil varistors are high-energy semiconductors made from silicon carbide that are used to protect against overvoltages in many applications. They're made of silicon carbide crystals, as well as some additives to fine-tune the electrical properties, all suspended in a ceramic matrix. A conductive coating is applied to the faces of the disc to provide the electrical contacts. It's the grains of silicon carbide themselves that provide the varistor behavior. Effectively, they have a high resistance with a low voltage across them, which drops as the voltage increases. At the specified clamping voltage, they have a very low effective resistance, which limits the voltage and dissipates the energy by allowing high current flow through the device. So now let's take a closer look at a Metrosil CTPU.
So here's a single-phase Metrosil CTPU device consisting of an SiC varistor disc, and you can see this in the picture on the right inside profile. The Metrosil varistor is in black and sandwiched into the heatsink assembly. The electrical connections are circled in blue, provided by two M5 bolts with lock nuts to take cable eyelets directly from the CT secondary winding. So in operation then, during a CT open circuit condition, the Metrosil CTPU immediately conducts, providing a voltage limiting burden. It dissipates a current through itself and its associated heatsink. On the picture at the left, in the front view, shows the thermal switches used to alert SCADA systems with a voltage-free, normally open switch condition. This is used to alarm engineers remotely of an open circuit condition, and in operation, the Metrosil unit thermally cycles and can be exposed to open circuit conditions for days on end without degradation or without risk of in-service failure. So here's our example from earlier. You'll see both CTs are protected by Metrosil CTPUs directly in parallel across their secondary windings. And during normal non-fault operation, there's a very small leakage current through the Metrosils, which remain passive and present a very high resistance. So they don't interfere with the function of the protection relay, which itself would require a separate overvoltage protection. And we'll have a little bit more later on in a later slide. So just to add, in application, for the best protection, Metrosil CTPU should be fitted as close to the CTs as possible to protect the cabling.
So this example shows the open circuit conditions from before, but this time with CTPUs fitted. So dangerous open circuit conditions are avoided as the CTPU instantly acts as a voltage limiting burden to protect the transformer. So we've covered what CTPUs are and how they offer protection to CTs during open circuit conditions. But what do the IEEE stipulate as best practice to ensure adequate protection for current instrument transformers?
Well, in IEEE C5713 standard requirements for instrument transformers under section 6.7.1 titled Operation with Secondary Circuit Open, we've extracted 5 salient points from this section and listed them in this slide. The first being, current transformers should never be operated with the secondary circuit open because hazardous crest voltages may result. Secondly, transformers conforming to this standard should be capable of operating under emergency conditions for 1 minute with a rated primary current times the rating factor, and the secondary open circuit if the open circuit voltage does not exceed 3,500 volt crest. When the open circuit voltage exceeds 3,500 volts peak, the secondary winding terminals should be provided with a voltage limiting device, such as a varistor or a spark gap. The voltage limiting device should be able to withstand an open circuit condition for 1 minute without damage to the secondary circuit. And the voltage limiting device may need to be replaced after such an abnormal condition. So just to say here, the Metrosil CTPU protection solution far exceeds this standard. We have a range of devices to clamp to most over voltage requirements, and we're able to operate for days rather than minutes under open circuit conditions in very high ambient temperatures without degradation, and we require no maintenance or in-service replacement. We have operational devices in the field for many years.
Thanks, Dom. So Dom mentioned spark gaps there, which were used as an earlier method of protecting CTs. Now, these graphs are from some work presented at DPSP conference a few years ago, comparing Metrosil CTPUs and spark gaps over prolonged open circuit conditions. Now, on the left, the Metrosil CTPUs remain constant over 100 thermal cycles, while the spark gap on the right immediately begins to degrade. After only 65 cycles, the voltage at which the spark gap activates has dropped below 25% of its original rated value. Now, spark gaps also produce lots of RF electrical noise, which can affect sensitive monitoring equipment in the vicinity. But Metrosil CTPUs remain consistent and offer long-standing protection, even in the event of prolonged open circuit conditions.
Yeah, that's a very good point on noisy spark gaps and protection voltage degradation there, Tom. So here's just a snapshot of our many end users, utilities, district network operators and national grids using Metrosil CTPUs. And the list grows as new power infrastructures are developed and the value of installing Metrosil CTPUs is recognised as a fit and forget protection for CTs. Our original CTPU is a mandatory device for many national grids and is specified with its full brand name, Metrosil CTPU, and many utilities and power companies will not accept alternatives. So a question we get asked quite often is whether it's possible to use Metrosil CTPUs with Metrosil relay protection in high impedance schemes, such as the one we were showing earlier in the slide. So Tom will cover that now.
Thanks, Tom. So here again, we have the example from before, but with a Metrosil relay protection device in parallel with the relay. So it's important here to clarify that Metrosil CTPUs act as protection solely for the secondary open circuit condition on the CTs. They don't interfere with the protection relay, but more importantly, do not offer protection to the relay. If the scheme calculation requires it, the protection relay needs its own overvoltage protection Metrosil, like we have here. So typically, at the relay setting, stabilizing voltage is lower than the voltages at which the CTPU will readily conduct, and so the CTPU remains passive. There will, as Dom mentioned, be some small leakage current which might need factoring in. However, examples of these are shown in Table 3 of our CTPU datasheet, which we will go through shortly. Now, when the relay trips due to a fault and a temporary overvoltage occurs on the protection circuit, the relay protection Metrosil kicks into gear and dissipates this overvoltage. As the CTPU is a higher impedance device, it only partially conducts, sharing a small portion of the TOV energy but not fully activating. It is only when the burden is disconnected and the primary is still energized that the CTPU fully comes into action. So using both relay protection and CTPUs together is not only fine, but recommended as a complete and complementary protection system.
So now we've covered the importance of using a Metrosil CTPU. The next stage is to choose the right specification for your current transformer. And we'll now run through a simple step-by-step process as you'll find on the Metrosil CTP website and the datasheet for selecting an appropriate device. Like I said, the datasheet is downloadable from metrosil.com. So there are 6 single-phase and 6 3-phase standard Metrosil CTPU types that can accommodate a range of burdens and operating conditions, and they're referenced by letters A, B, C, or 4 digits. And for every single phase device, we have a corresponding 3-phase device, which has a different set of specification numbers. So the procedure is quite simple. Step 1, identify the CT application. So for either metering or measurement, use Table 1. Or for protection, use Table 2. So for this webinar, Tom will take us through an example of a protection CT with its in-application specifications. So we're going to be looking at a 1 amp CT with a 30 VA burden with 100 volts RMS in application secondary voltage under normal conditions and a protection voltage of less than 3000 volts peak.
Yep, so to select the Metrosil type, we need to use the CT burden, the rated secondary current, and the maximum fault current as a multiple of the rated current. So in this example, we're using a CT burden of 30 VA, a rated secondary of 1 amp, and a maximum fault current of 20 times nominal. So we're going to select a 3134 here. Next, you need to check the normal voltage across the CTPU is low enough to avoid thermal cycling. Using the graph, check the voltage across your CT due to wire and burden impedances, and check that this corresponds to a dark blue cell for the chosen CTPU type. This means the unit will not be thermally cycling under normal conditions. For our example, we're okay as the secondary voltage across the terminals is 100 volts and a 3134 can withstand that indefinitely. Now at this stage, if the values and times all look acceptable, you can move to the next step. If, however, they're outside of your requirements, then we recommend that you contact us for assistance or a bespoke design. And then finally, you just need to check that the chosen Metrosil CTPU would limit the voltage to a level that will not damage the CT. So in this case, our selection of a 3134 is okay, as the voltage it's limiting to is under 3000 volts. So I hope this example demonstrates how easy it is to specify a CTPU and the importance of making sure the details are correct.
Thanks for that, Tom, and hopefully those simple steps allow you to specify the right Metrosil CTPU for your application. We're always here to provide help and advice if you need us. Just send us an email, which we'll include at the end of this session. The Metrosil CTPUs are often supplied directly into OEM factories or schemes with existing protection cabinets. Sometimes the scheme requires us to provide a factory-built solution in pre-installed Metrosil CTPUs to a customer site. So M&I Materials manufacture a range of these enclosures which can be factory pre-fitted with the Metrosil CTPU of your choice. So this slide shows a range of our standard enclosures, so 4, 8 and 12s, providing a complete pre-assembled protection system for simplicity of supply chain, ease of installation, straight to site. And here we see the internals of a fully fitted 12 cabinet, and we provide a number of enclosure configurations based on our standard cabinet options. Each enclosure is type tested and independently certified to IEEE 61439 Part 2 with multiple terminal blocks for CT inputs and SCADA signal wiring outputs. Shows a diagram there on the left. And if you'd like more details on this, again, please contact us. Our details will be provided at the end of the webinar.
Okay, now we'll move on to why Metrosil CTPUs are the superior choice when it comes to CT protection.
So Metrosil CTPUs occupy the top of the range, preferred supplier status as the original CT protection device. And we have this because we have unmatched in-service reliability from millions of devices in critical protection schemes trusted around the world. And to do this, we constantly application test our devices within our Metrosil test lab with a custom power transformer and CT equipment. An example of our test circuits shown here. This custom test equipment allows us to compare Metrosil CTPUs directly with other types of protection and varistors on the market. And we found that not all varistors are equal. When subjected to thorough comparison testing with Metrosil CTPUs, we found other varistor-based devices failed. And our comparison testing revealed a range of defects shown in this slide, from complete failure to non-conforming ratings. And that's cause for concern, and it's to check when specifying CT protection that it is the original CTPU, a Metrosil CTPU. So in summary, we can say it's very important to note Metrosil CTPU was the original CT protection device, so beware of imitations or so-called equivalents. As we've found, they're not all the same. M&I Materials Metrosils are specified into projects for that very reason. All our Metrosil devices are QA tested, electric strength, dielectric strength high pot safety tested, and have full batch traceability. We have an extremely long service life when used within the device ratings. And for that reason, it's important to correctly specify the Metrosil CTPU by using our simple step-by-step data sheet. Again, you can download that from metrosil.com. And the Metrosil division at M&I Materials are factory audited by Siemens, ABB, Hitachi, GE, and other major electrical OEMs to ensure that our procedures and testing are acceptable to their high standards. We're very proud of our consistent A-class supplier status, and it shows the level of trust in Metrosil products, which is much needed in supply chain reliability and longevity, especially at the moment. So I hope we've shown Metrosil CTPUs as a premium choice for CT protection, and I hope this has been useful for all watching. Thanks for your time today.
Okay, thanks for that, Dom. I hope all of you attending have found the information presented helpful and that it's provided you with some useful insights that might influence how you specify CTPUs as part of your infrastructure. We've had a few interesting questions come in during the webinar, but time is running short, so I'll put 2 or 3 towards the team now. So with the first question, I have a multi-tapped CT, which winding do I connect the Metrosil CTPU to?
I can take this one if you like. So
Thanks.
yeah, it's quite straightforward. Yeah. Okay, so if you're using a single core CT, the whole of the secondary winding should have a Metrosil CTPU across it to protect the output, even if several taps are being used. And if your CT has separately wound secondary cores, so for example, separate measurement and protection cores, each core needs to be protected. So I hope that addresses that one.
Thanks, Dom. Another question here. I have calculated my CT knee point voltage and given this as a requirement for protection. Is this enough for you?
I can take that one. Yeah, so this is a good question. It's quite a common one we get asked a lot. We actually don't need to know what the CT knee point is to specify CTPU. All of the data we needed was mentioned in the previous slides, and it's on our data sheet. So all you need to do is follow those step-by-step instructions, and that should get you to the correct Metrosil device. So yeah, I hope that answers your question.
Brilliant, thanks, Tom. And just one more question. I have Metrosil CTPUs delivered to site for my CTs. How do I test these during substation commissioning?
I can do that one as well. So again, this is a very, very common question. It's a good question to ask. So because of the non-linear nature of the devices, it's actually quite hard to test them in the field. A digital voltmeter or an ohm meter will give you a very high and variable resistance when you test these devices, and also will give sort of wildly different values between devices. So it's not a useful metric to test them. The best advice we can give is a good visual check for physical damage or transit damage before you install them. So Metrosil CTPUs are application tested, all of them before dispatch, and this is all factory audited. So, and if required, we can provide certificates of conformance to this. I hope that answers your question.
Brilliant, thanks, Tom. So that's all we've got time for question-wise, and there's still some here to answer. Thanks to those of you that have sent questions in. For those that haven't been answered, Dom or Tom will come back to you directly. Alternatively, you can always send in a question to them using the contact details provided on this screen, and we'll make sure that you get these contact details sent in a follow-up email as well. So thanks, Dom, for today's presentation on Metrosil CTPUs, and thank you all for joining us. If you have any colleagues who've missed this session who you think would be interested in the content, please look out for the webinar recording, which we'll send out to you soon. So thanks again for your time today. Stay safe, and we look forward to seeing you again for a future technical webinar.